I'm sure you believe that it is the photon which actually kills a cancer cell. If you think so, you are 100% wrong. The real weapon is someone else. It is certainly not photon. I'm also sure that you treat the linear accelerator like a black box. You think when a button of linear accelerator is pressed, photons comes out of it, hits cancer cells and the cancer cell die. If you think so, you are 100% wrong again. Radiation is not magic. It is exact, violent physics. Today we are going to track that real weapon. I will teach you the epic journey of a photon right from its birth to ultimate DNA damage. I will take you through the 10 steps of radiobiology of this entire journey of a photon life. If you don't master these 10 steps 100%, your foundation for radiation oncology will be weak. What you are going to learn today in this lecture will change how you see radiotherapy forever. Let us begin. Hello friends, before we begin, for those who are new to this channel, I am Dr. Parveen Ahlawat. I am a consultant at Rajiv Gandhi Cancer Institute and Research Center in New Delhi for over 12 years. I have been practicing and teaching oncology for more than a decade. I did my MBBS and post-graduation from CMC Vellore. Then I did my DNB at Rajiv Gandhi Cancer Institute and Research Center, New Delhi. I pursued a fellowship at the Royal Marsden Hospital in London and have later undergone specialized training in cyberknife from the United States. I have published almost 85 research articles and abstracts in PubMed indexed international journals. Welcome to the most important lecture of your residency. Let me ask you a very simple question. How does an X-ray photon actually kill a cancer cell? I know what you are thinking in your mind. You think you know it well, or at least have some idea about it. You believe that when a linear accelerator is turned on, a powerful photon comes out of its gantry head and goes inside the patient and kills the DNA. If this is what you thought, let me tell you, you are completely wrong. This is the fundamental misconception among newly joined radiation oncology residents. If you tell this to your examiner in your final DNB or MD Viva, the examiner will fail you immediately. This will clearly show that you have not understood the journey of a photon right from its birth to its finally causing DNA damage. Listen, photon itself does not directly damage the DNA. Did you know this? Once again, photon itself does not directly damage the DNA. A photon from linear accelerator machine cannot simply travel and destroy a cancer cell on its own. It is physically impossible. When you look at a linear accelerator, it looks very quiet and a very peaceful machine. It hardly makes any sound. Every electrical connection, hardware and software seems perfectly silent. The X-ray beams which is coming out of the gantry head is also completely invisible. But do you know what is actually happening inside the atom of a patient when the beam is on? There is a violent and invisible war. At atomic level, it is a war zone. See, lethal damage of DNA of a cancer cell is not a single event. It is the final results of a strict multi-stage physical and chemical sequence. To understand the entire chain of events, I have broken it into 10 steps. These 10 steps will actually cover almost half of your radiation physics and half of radiobiology you need to know as radiation oncologist. There is no textbook which has summarized this sequence. If you do not understand these exact 10 steps in your sequence, your clinical foundation about radiation oncology will be dangerously weak. You are simply guessing. In this video, I am going to take you through the epic journey of a life of photon, starting from the moment a photon is born to the final event, DNA damage. Pay very close attention. I will show all 10 steps one by one. It is going to be a half an hour lecture, so keep patience. What you are about to learn today will change how you see radiotherapy forever. Before we look at the first step, I want to show a timeline of this entire 10-step multi-stage process, starting from the birth of a photon to DNA damage. Can you guess how much time it takes to complete all these 10 steps? When you press the beam on button on your linear accelerator, how fast does the damage actually happen? The physical birth of the photon and the violent Compton effect happen in 10 to the power of minus 15 seconds. Yes, you heard it right. Only 10 to the power of minus 15 seconds. The chemical generation of the deadly free radicals is completely over in just 10 to the power of minus 9 seconds. Yes, you heard it right again. Now listen to me very carefully. It is very important. The physics and chemistry of the entire multi-step process are finished in less than 1 single milliseconds. It is a fraction of a second, so unbelievably small, the human brain cannot even comprehend it. Now think about your two main textbooks you must memorize for your exams. Eric J. Hall's for RadioBiology and Faizam Khan for Radiation Physics. These are two massive, heavy books filled with hundreds of pages of complex science. Here is the most shocking fact of your residency. Almost the entire, both of these books are written just to explain what happens in that one invisible, very, very small fraction of a second. Hundreds of pages in these two books are written to explain what happens during this very, very small fraction of a second. Isn't it shocking? Now listen carefully again. While the physical and chemical impact is instantaneous, happens in milliseconds, the biology requires extreme patience. The cancer cell does not die on your treatment table on your linear accelerator. It continues to live, function, and make its usual proteins as if nothing has happened. The ultimate mitotic death of a cell can take hours, days, months, or even years to happen. Now that you understand this timeline, let us now dive deep in all the way in and see exactly how this journey begins. Let us move to step 1. This is very first step. This step is actually the birth of the photon. Birth of the photon. You might think X-rays are produced by electrons simply smashing into a metal target. This is a massive oversimplification of this step. If you say that in Viva exam, you will look foolish. So what exactly happens in this step? Look, inside the linear accelerator, an electron gun fires a high-speed electron at a heavy tungsten target. This is shown in this image. The red dot you can see represents a negatively charged electron coming from cathode or electron gun, at high speed towards the atom. This is nucleus, which is positively charged. Yellow color line is the track or path of this incoming electron. As electron comes closer and closer to the atom, it interacts with the intense positive electric field of the target nucleus. Because of this massive positive charge, it creates an extremely strong electrostatic pull on this negative incoming electron. This invisible force of attraction is incredibly powerful at such a close distance. As the negative electron passes near the positive nucleus, it is pulled off its straight path. It is forced to sharply bend its path. Electrons now have to slow down. Think of this just like driving a fast car on a highway. What happens when you suddenly make a very sharp turn? In order to survive that sharp turn, you must slow down your car. It is like applying sudden brake. The exact same physics principle applies to this high-speed incoming electron. When it takes a sharp turn like this, it has to slow down. As it slows down, it instantly loses a massive amount of its original kinetic energy. This lost kinetic energy cannot just disappear. It is instantly converted and emitted as an X-ray photon. This is called as Bremsstrahlung interaction. Bremsstrahlung is a German word that simply means braking radiation, like applying brake in the car when you take a sharp turn. So this is the birth of an X-ray photon. The photon is born now. Don't think this photon will go and hit DNA and cause damage. There are many steps before that happens. But there are two major problems here you must remember at this step 1. The first one, this entire process we just saw is very inefficient. Why? Because 99% of this energy go waste. It is lost as heat. It is only remaining 1% which actually makes our therapeutic X-ray photon beam. Only 1%. This is the second major problem we face. Many residents assume the linear accelerator produces a clean and perfect beam of radiation. This is how a spectrum of an ideal beam of radiation look like. This ideal beam would only contain photons at a single high energy level. But you know, ideal things don't exist. That is why they are ideal. In reality, we get this spectrum of X-ray radiation. This represents the raw, unfiltered beam produced by Bremsstrahlung. X-axis shows the increasing energy. Y-axis shows the increasing amount of X-rays. Notice that this spectrum is completely dominated by weak, low energy photons. These are called soft X-rays. If this raw beam strikes your patient, these weak photons will never reach the deep tumor. They will be entirely absorbed by the superficial tissues. They will cause severe skin toxicity without any clinical benefit. We need to create a better beam. Our machines cannot naturally produce this ideal beam. So we must artificially create it. We have found a solution for that. The solution is to place a physical metal filter in the path of unfiltered raw X-ray beam. Filter. These filters are usually made up of materials like aluminum or copper. Place it like this here. See what happens once we introduce a filter here. What actually does this metal filter do? It acts as a ruthless physical barrier. It selectively absorbs those dangerous low energy photons. This physical filtration process is called beam hardening. Beam hardening. Remember, examiners will strictly look for the exact textbook terms for this process. Beam hardening. By stripping away the weak photons, the filter shifts the average energy of the beam much higher. The maximum energy stays the same, but the overall average energy increases. This is exactly how we optimize clinically safety and increase the penetrating power of the beam. Now we finally have a powerful and penetrating megavoltage X-ray photon beam. This hardened beam is clinically safe and highly useful. It is now ready to exit linear accelerator machine and strike the patient. This slide shows how the filtered beam looks when compared with unfiltered raw beam. See on the right graph. This is what we actually get in reality. We get a pure monoenergetic beam of photons that penetrates deeply and safely into the patient. The filter has completely stripped away the dangerous low energy X-rays. Because these weak photons are removed, the average energy of the entire beam shifts to the right. This exact physical process is called beam hardening. Memorize the shape of these three beams. Don't worry if you have not understood this concept. I will cover it in detail in my next videos. This is another diagram to explain you same things. You can see unfiltered raw X-ray beam coming from top like this. We place a filter here. These filters selectively absorb those low energy photons. This process is called beam hardening. Now we finally have a powerful and penetrating megavoltage X-ray photon beam. This hardened beam is clinically safe and highly useful. It is now ready to exit the linac and strike the patient. Let us move on to see the third step. The hardened therapeutic beam or filtered beam we just created finally leaves the linear accelerator. See here in this animation. It crosses the physical air gap and enters the patient. Now see this image. This is air or space between linear accelerator and the skin surface. This is skin surface. This is an important edge. The edge between the air and skin surface. Rest of the region is a deeper portion of tissue of the body. See what happens next. When a photon enters skin, they safely penetrate deeply and spare the skin. Photons do not deposit its 100% energy at skin surface. This is called skin sparing effect of X-ray photon beam. This skin sparing is not because photons simply ignore the skin surface. This is a very common and very dangerous myth most residents suffer from. Photons absolutely do interact with atoms right at the surface of the skin. But you must remember our rule from step 1. Photons are indirectly ionizing radiations. Photons are indirectly ionizing radiation. Because they have zero mass and zero charge, they cannot drop the heavy clinical dose themselves. Rather, what they do is they interact at the skin surface and eject high-speed secondary electrons. Photons interact at the skin surface and eject high-speed secondary electrons. These energetic electrons must travel a short distance forward into the tissue before they drop their maximum energy. This exact physical phenomenon is called dose buildup. The true peak dose happens at this specific depth deep inside the tissue, not at the skin surface. This is the real textbook reason we achieve skin sparing with megavoltage beam. You must explain dose buildup to the examiner, not just say the photon pass through. The moment the beam enters the skin and goes deep into the tissue, its overall intensity begins to drop. See this. This continuous drop in beam intensity is called attenuation. The photon is now ready to interact with the tissue atoms. Now we reach step 4. This slide shows the 3 main ways a photon can interact with human tissue. This is an entire chapter in radiation physics. It comes as a straight 10-mark question. I will teach you these in my later videos. But for now, let us see it briefly. These 3 main ways a photon can interact with human tissue are photoelectric effect, Compton effect, and pair production. Some of you may think they are all equally important in your daily clinical practice. This is where most first-year residents fall into a major viva trap. They are not. If an examiner asks you which interaction dominates our megavoltage treatment beams and you say the photoelectric effect, your viva is over. The photoelectric effect is only dominant at a very low diagnostic energies, such as for diagnostic purposes such as taking X-rays, mammography, etc. But we are not here to take diagnostic pictures. We are here to destroy deep-seated tumors. Pair production is also not our primary weapon. It requires a strict minimum physical threshold of 1.02 mega electron volt just to even begin. The absolute dominant process in modern radiotherapy is the Compton effect. Compton effect. For standard megavoltage beams treating soft tissues, the Compton effect is the king. In the Compton effect, the incident photon interacts with a loosely bound outer electron. Because it is so loosely bound, we call this a free electron. Because the binding energy of this outer electron is so small compared to our high energy photon, we call it a free electron. During this collision, the photon does not disappear. It gives up only a portion of its energy to the electron. The original photon then scatters in a new direction. It continues to exist, but with reduced energy and a longer wavelength. The target electron absorbs the transferred energy and is forcefully ejected. We call this the Compton recoil electron. The scattered photon can bounce in almost any direction, but the ejected electron is strictly confined to forward angles between 0 and 90 degrees. This specific collision is the absolute engine of modern linear accelerator machine. Step 5. This is one of the most fundamental concepts in all of radiobiology. Look at the screen very carefully. We are talking about indirect ionization. Many junior residents completely misunderstand this term. You might think the photon itself travels through the cell ripping electrons away from atoms left and right. This is physically impossible. Remember, our therapeutic photon has no mass and absolutely no electrical charge. Because it lacks a charge, it cannot pull or push other electrons away from their orbit. Therefore, it cannot cause significant ionization on its own. It is classified strictly as indirectly ionizing radiation. It must use a strict two-step process to destroy the cancer cell. Step 1 is the primary interaction, which we just saw in the Compton effect in previous slide. The uncharged photon interacts with the tissue atom to forcefully eject a charged electron. This is all that a photon does. It simply creates the weapon. Step 2 is where the real action begins. The ejected charged particle, which we call the secondary electron, now takes over. Because this secondary electron has both mass and a negative charge, it is highly destructive. As it travels through the tissues, its negative charge strongly repels other electrons away from their atoms. This causes the vast majority of the ionizations along its path. If the examiner asks you, what does the actual ionization work in X-ray therapy? Do not say the photon. You must confidently state that it is the secondary electron. Secondary electron. Now we reach step 6. We have finally found the real weapon of this entire multi-step process. Secondary electrons. You might still be thinking about the original photon. Forget about photon now. The forcefully ejected secondary electrons now takes complete control. It travels like a high-speed bullet deep into the tissue. Because it has mass and a negative electrical charge, it repels other electrons. It forcefully rips them away from their stable atoms. It causes thousands of violent collisional ionization along its path. This single electron is the primary agent of physical destruction. It does the actual dirty work what the photon could not do. Look at this slide very carefully. Examiners love to test you on exactly how this energy is dropped in tissues. We call this measurement linear energy transfer or LET. LET simply means the amount of energy deposited per unit of microscopic distance the particle travels. Listen now. As the secondary electron travels, it deposits its kinetic energy along its track. The specific rate at which it drops this energy per unit of distance is called linear energy transfer or LET. Once again, the specific rate at which it drops this energy per unit of distance is called linear energy transfer, LET. This slide compares two very different types of energy tracks based on this concept. First, see low LET X-rays. The secondary electrons created by our standard therapeutic X-ray beam we use commonly in our linear accelerator belong to these low LET radiation. They travel in a random zigzag path and deposit very little energy at any one spot. Because this energy is so spread out and sparse, you need about 1000 of these tracks to deposit just 1 gray of radiation dose. They leave a scattered and very thin trail of energy. Scattered and very thin trail of energy. Their path is irregular and they drop energy very thinly along the track. Now look at the high LET X-rays. They are heavy particles. Heavy particles such as proton, alpha particles or carbon ions are massive. They do not bounce around easily. They travel in a straight path and drop a very thick, dense column of energy along its track. We call this high LET radiation. Because the energy is packed so tightly together along the track, you only need about 4 of these dense tracks to deposit the exact same 1 gray of dose as compared to 1000 tracks with low LET radiation. In simple terms, low LET X-ray radiation leaves scattered, relatively sparse damage. High LET radiation such as heavy particles leaves dense, highly concentrated damage that is incredibly difficult for the cancer cell to survive or repair. It is the only way you will understand why some tumors easily repair X-ray damage but cannot survive heavy particles. Now let us move on to step 7. This is step 7. Here is a question I will ask you. What is the primary target of this high-speed secondary electrons? If you say DNA, you are wrong. Look at the slide. The human cell is composed of at least 70 to 80% of water. This means the electron will almost always smash into water first. The secondary electron is far more likely to strike water molecule than the DNA. This is pure statistical probability. When the electron strikes hard a water molecule, it transfers an immense amount of kinetic energy. This energy drastically exceeds the stable binding energy of the molecule, fracturing its stable chemical bonds. The water molecule is literally blown apart. See here. This exact physical cleavage of water molecule is called radiolysis of water. Radiolysis of water. You must memorize this term. This is the exact moment the physical stage of radiation ends and starts chemical stage. Now onwards, in further steps, we will talk only about what happens at chemical levels. Now we reach step 8. The physical stage is over and the chemical stage begins. This process creates free radicals. Free radicals. You must be very clear about free radicals. Many residents talk about free radicals all the time, but they cannot define them exactly. If the examiner asks you, you must give the exact textbook answer. A free radical is an atom or molecule with an unpaired electron in its outer shell. This single unpaired electron makes it highly unstable. It is this unpaired electron which makes it highly unstable and reactive. It is very reactive. It wants to eat or consume an electron from anything nearby to become stable again. Breaking the water molecule creates two main agents. These are hydrogen radical and the hydroxyl radical. Hydrogen radical and the hydroxyl radical. Here is your next question. Here's the next big question, exam question in Viva. Which of these two free radicals actually does the lethal damage? It is the hydroxyl radical. The hydroxyl radical is the true lethal weapon. You must also know its lifespan for the examiner. It only exists for 10 to the power minus 9 seconds. But in this very short time, it travels just far enough to reach its target. This free radical is now ready to attack the DNA. Let us move to step 9. This is step 9, final attack on DNA. This slide shows two different ways we can attack the DNA of a cell. One is called the direct action and other is called indirect action. Direct action, indirect action. Very important concept. You must know exactly which action your linear accelerator uses. Let us look at direct action first. In direct action, the high-speed secondary electron hits the DNA directly. It physically cuts the DNA chain all by itself. But here I have a surprise for you. This direct action is not the main way how radiation kills cell. Direct action is the primary weapon for heavy particles such as proton, carbon ions or alpha particles. Now look at the indirect action. This is what we actually use for killing a DNA. In indirect action, the electron smashes into water molecule first. It creates the highly unstable hydroxyl free radical. Then this free radical hydroxyl ion travels to the DNA and attacks it. Listen to me very carefully. For standard X-ray beams, which we commonly use in our linear accelerators or telecobalt machine, indirect action is the dominant and main mechanism of action. In fact, 70% of all DNA damage is caused by this indirect action. A mistake residents often do is they tell the examiner that X-ray beam directly cuts the DNA. If you say so, you will fail. You must confidently state that indirect action is what truly kills the tumor. Let us move to step 10. This is step 10. The lethal chemical weapon has finally reached the target. It attacks the DNA. But here is your next major viva trap. Examiner will ask you exactly what type of DNA damage kills the cancer cell. Radiation causes roughly 1000 single strand breaks in a cell. If you tell the examiner that a single strand break kills the cell, you will fail immediately. A single strand break can be easily fixed. Every cell has a mechanism to repair such single strand damage. The cell simply uses the opposite healthy strand as a template to repair the damage. It is of almost no biological consequence for cell killing. To truly kill a cancer cell, you must create a double strand break. Double strand break. This happens when both strands of the DNA helix are broken directly opposite each other, or when they are broken just a few base pairs apart. Listen once again. This happens when both strands of the DNA helix are broken directly opposite each other, or when they are broken just a few base pairs apart. When this happens, the DNA strand snaps completely in half. The chromatin is cleaved into two separate pieces. This double strand break is the absolute most important lesion in all of the radiobiology. It is the ultimate lethal damage we need to destroy the tumor. So the DNA is broken now, but here I have a tricky question for you. When exactly does the cancer cell dies? Many of you who are beginners in radiation oncology residency think the cell dies instantly while the patient is on the treatment couch and we turn on the start button of a linear accelerator. You are completely wrong. The cell does not die instantly on the treatment table. Listen carefully now. A cell can survive for hours, days, weeks, or even months. It can even continue to function normally. But it is a walking dead cell. Walking dead cell. Its fate is already sealed and fixed. Because of that double strand break, the chromosomes have been damaged. They fuse together to form lethal aberrations such as dissects, rings, or anaphase bridges. When this cell having damaged chromosome finally tries to divide, it cannot separate its DNA. The chromosomes are stretched and torn apart. See here. This is called mitotic death. A very important term for you to remember right now. For almost all solid tumors we treat, this is the absolute primary mechanism of cell killing. The cell dies while attempting replication. And with that, the epic journey is complete. From the birth of the photon inside the machine to the ultimate destruction of the cancer cell DNA. If you understand this 10-step sequence, your clinical foundation will be solid. Each of these 10 steps are separate chapters in itself in your radiobiology and physics books. We will cover those in our videos later. Okay friends, I know it has become a long lecture explaining this epic journey, but I feel I must summarize all 10 steps here. This is the summary. Take a screenshot of it and understand it 100%. This slide takes us through the journey right from the birth of a photon to the DNA damage. Step 1 begins with the birth of a photon. Here, in this step, high-speed electrons bombard a heavy tungsten target. More than 99% of the kinetic energy is waste and lost as pure heat. Only approximately 1% survive to become actual X-ray photons. Step 2 is beam filtration. The raw and unfiltered X-ray spectrum of radiation is highly useless, rather dangerous. It must pass through filters made up of aluminum or copper sheets. These filters strip away the useless low energy photons, shifting the mean energy of the beam upwards. Step 3 is the exit of a photon from the linear accelerator. The photon breaches the vacuum of the machine and enters the patient's body tissue. Step 4 is the Compton effect. At megavoltage energies, the primary high energy photon smashes into a loosely bound outer electron, giving up its energy. Step 5 is indirect ionization. This uncharged photon knocks out a charged electron, triggering a violent chain reaction. Step 6 introduces the real killer or weapon, the secondary electron. This secondary electron leaves a thin zigzag trail of energy. Because it has negative charge, it rips through the cell, causing thousands of ionization along its path. Step 7 is the collision of secondary electrons with water molecules. The electron almost always crashes into water because it is the most common molecule in the cell. This collision damages the stable chemical bonds. Step 8 is the generation of free radicals. Radiolysis of water molecule creates the true chemical weapon, the highly reactive hydroxyl radical ion. Step 9 represents the actual biological mechanism of action. Indirect action is the absolute dominant force. The free radicals aggressively attack the DNA structure. It is this indirect action which accounts for approximately 2/3 of the total damage. Step 10 is the final execution, DNA damage and mitotic death. This chemical attack breaks the DNA in half, creating a lethal double strand break. The cell's repair pathway cannot handle this much cluster damage. When the damaged cell tries to divide, it is finally destroyed by mitotic death. Mitotic death. This concludes our epic journey of the photon. Dear friends, master these 10 steps 100% on my channel to make your foundation strong. I will teach you all of these during my lectures. Friends, we have now discussed all the 10 steps in detail, but reading the theory is not enough. You must be able to visualize this entire 10 steps of invisible war in your mind. To help you do exactly that, I have prepared something special. I have created a highly detailed 5 minutes video. This video beautifully summarizes the entire 10 steps I just taught you. It will show you the epic journey of photons right from its birth to the ultimate DNA kill. I am going to play this video for you right now. Enjoy and watch this video closely. I'll finish my talk here. Let us watch the video. I will see you in next video. Thanks for watching. Signing off, Parveen Ahlawat.
When you walk into a treatment room, the machine looks perfectly silent. There are no sparks or loud noises. Because of that, most people imagine radiation is like a hot laser, just a beam that comes out of the machine and burns away cancer cells on contact. Inside the patient's body, the situation is much more violent. At the atomic level, it is an invisible war zone. Every time the beam turns on, it triggers a strict 10-step chain reaction that is entirely finished in less than a single millisecond. This journey starts with a screeching halt. Step 1 is the birth of our first messenger, the X-ray photon. Inside the machine, an electron is fired at a heavy metal target. As it gets close, the intense pull of the target forces the electron to take a sharp turn. Just like a car slamming on its brakes to make a tight corner, the electron loses a massive amount of energy. That lost energy is instantly released as a brand new wave of light. This microscopic braking process is the exact moment the primary weapon is born. This chart shows the energy of the beam immediately after it's born. It's a messy, chaotic mix. Most of these waves are actually quite weak. If we let them hit a patient, they would be absorbed instantly by the skin, causing severe burns, without ever reaching the tumor. To prevent this, we force the beam through a physical metal filter. This filter acts like a bouncer. It strips away all the weak energy, which shifts the average power of the beam much higher. This creates a uniform, mega-voltage beam that is powerful enough to penetrate deep into the body. In step 3, this hardened beam finally crosses the air and enters the body. Because we stripped away those weak waves, the energy safely bypasses the surface of the skin without dropping its destructive payload there. By tuning the beam to ignore the skin, we ensure the energy infiltrates deep into the patient, setting the stage for an internal attack that the tumor won't see coming. The beam is now inside the tumor, but here is the catch. That X-ray photon is physically incapable of destroying a cancer cell on its own. It has no mass and no electrical charge, so it has no way to actually push or pull an atom apart. Step 4 is where the handoff happens. The incoming photon crashes into a tissue atom and transfers its energy to a loosely bound electron on the edge. It violently knocks that electron completely out of its orbit. The photon's only job is to provide this initial push. It creates the weapon, then effectively disappears from the story. Now we meet the real killer. Step 6 introduces the secondary electron. Because this particle has mass and a negative charge, it acts like a high-speed bullet. It tears through the tissue, using its charge to rip other neighboring atoms apart as it flies by. This diagram shows 2 ways energy can be dropped inside a cell. Standard X-rays create electrons that travel in a thin, zigzag path, leaving a trail of scattered dots. Heavy particles, on the other hand, plow straight through like a fire hose, leaving a thick, dense column of destruction that is much harder for a cell to survive. The original photon was just a phantom trigger. It is this newly created chaotic secondary electron that does the actual work of destruction inside the tumor. So what does this speeding electron actually hit? A human cell is about 80% water. By pure statistical probability, that electron is going to crash into a water molecule long before it ever finds a strand of DNA. Step 7 is the collision. The electron slams into the water with immense kinetic energy, physically shattering the chemical bonds holding the molecule together. This creates step 8, free radicals. These are jagged fragments of water that are missing an electron. They are incredibly unstable and desperate to steal a new electron from anything nearby just to become stable again. This is the moment where physics ends and chemistry begins. These reactive fragments begin to travel rapidly through the cell, hunting for the cell's most precious asset. This is the genius of the process. Radiation doesn't bring its own poison into the body. It turns the cancer cell's own water into a temporary chemical weapon. The free radical finally reaches the DNA. If it only manages to snip one side of the ladder, the cell will simply repair it and keep growing. To a cancer cell, a single strand break is just a minor inconvenience. Step 10 is the final strike. The goal is a double strand break. This happens when the chemical fragments attack both sides of the DNA helix at the exact same spot. The instruction manual snaps completely in half. Even though the damage is done, the cell doesn't die while the patient is on the treatment table. It stays fully functional, acting like a walking dead cell for hours, days, or even months. The end finally comes when the cell tries to divide. Because its instructions are snapped in half, it can't figure out how to duplicate its DNA. And as it tries to pull itself apart to create a new cell, it literally ruptures and dies. This invisible relay race, from a photon's birth to shattered water and snapped DNA, succeeds by planting a microscopic time bomb that ensures the tumor's eventual destruction.